Okay, I guess we're ready to start the last talk for the day. So we have Saskia, who's going to tell us about topological defects and generalized T-duality.
Thank you, Linus. First, I would like to thank the organizers for this invitation to speak, but also for organizing this very nice conference. So today I want to present some work that we hope is nearly finished about topological defect and generalized T-duality. And this work in collaboration, where is the... with Thomas Raml, that should be sitting somewhere here. Okay. So first, let me give some motivation, and I am lucky that I am on the third day of this conference, so you all have actually had pieces and bits of all these connected concepts that we have at this conference, so that we try to find integrable models that are deformed, have less symmetry, but are still integrable. And it is somehow related to this generalized notion of T-duality, which is known as Poisson-Lie T-duality. And that we can formulate that into double field theory and generalized geometry. And that maybe for some of us, the ultimate goal is to find some deformed version of ADS CFT where we have less symmetry, but we still have integrability. And the question I want to ask is, what happens to all these relations and all these bubbles when you add defects into the picture? And defects are very rich objects. They have different appearance, they have different definitions. So actually, you will also use different defects in different of these sides. So for example, for integrable deformations, you might wonder, well, we already have deformations inside the system. Can we add on top of that defects and still remain integrable? And actually, I answered this question already with Thomas, actually partially by constructing explicit example of defects that indeed deform these Yang-Baxter deformations. But today, I would like to focus on the other side of this slide and try to see whether we can find a certain type of defects, which are called topological defect, that encodes this generalized notion of T-duality and what its consequences are. Okay. So just to brief you a brief outline of what's going to come. So first, I need to introduce what the defects are and what topological defects are in particular. And then once I've done that, I can explain how I can realize Poisson-Lie T-duality in terms of a topological defect. And the rest of the talk essentially will be about application and consequences of having these objects. But at the end of the talk, actually, I want to make a more general statement and walk away from a Poisson-Lie T-duality and study something that's known as the notion of fusion on a more general level. Good. So, well, I think that you all have a rough idea of what a defect is, but let me be a bit more precise. So, I mean, simply when you have a slab of material, that material might have different phases on which it is. And these different phases then are separated by some boundary. And so that is our defect. So it's a kind of internal boundary for which the fields inside your system might change discontinuously, but it's still the same slab of material, so it should preserve certain properties. So in our case that we will look at, we will actually have two worldsheets, and they both describe a different model, and they will be separated by a line defect. And depending on what kind of properties they will preserve, they will have a different name. So you have conformal defect, you have topological defect, and you have integrable defect. And I would like to focus on topological defect. So maybe before I get questions about this, let me be clear that, so for example, integrable defects, they do what you think they do. That is that when you put them there, integrable defect will preserve the integrability of the whole system. So the two models plus the defect. On the other hand, conformal and topological defect do not, I mean, these adjectives do not refer to the whole system as a whole, but actually about special properties of the defect itself. So speaking about topological defect, I'm not speaking about topological systems. Good. But I actually want to restrict what kind of model we are looking at. So I will be looking at sigma models, like we had quite a few times already in the talk. And so that means that I will have a total system with, well, on the left, say, a model which is defined by a target space X from sigma to a target space M. Then another model that goes from sigma tilde to M tilde. And then I can see this thing as living in this product space. The product space is a product of the two target space. And then I need to take into account that the bulk fields on the two sides have to couple to this defect via a line bundle that has a connection A. And here it comes with a pullback. Perfect. So that's the setting. But actually, I do not want to work on a worldsheet. I want to work at the level of the target space, because there, at least for Poisson-Lie T-duality, I understand things better. And so what is then the topological defect in a target space? Well, then you just take this line, you map it through the target space map, so the product that you have now, and so it's going to span a submanifold in your product space, which are called Y, together with the induced line bundle that comes from the one on the worldsheet, which I will denote by the same letters. But okay, so still I want to preserve my certain properties, which are for us calculability. So the fact that it will be topological in particular will impose strong constraint on this pair that will determine the topological defect in the target space. So, and this I will explain a bit later in the talk. But first, let me say what topological defects are for the worldsheet. So there, a topological defect means that the holomorphic and anti-holomorphic components of the energy momentum tensor are going to glue nicely on the location of the defects. And okay, so what does that have an implication? Because that makes the topological defect interesting. Well, the name topological comes actually from one of these properties, because one of these properties implies that you can actually deform and move the defect at no cost. So it's a line, and you can do whatever you want. You can deform it. And one of the things we will be able to do is a concept of fusion, where we're going to joint defects together or joint with boundary conditions in one of the models. But that will be for the second half of this talk. What the other nice properties that is generally expected from these topological defects is that they encode symmetries or dualities between systems. And at the level of the worldsheet, this has been studied a lot by a lot of people, and it has been shown to realize abelian T-duality, Kramers-Wanier T-duality in more condensed matter settings, or theories that are all false on each other. And these are just a couple of examples. On the level of the target space, when you don't have that much control on the worldsheet, it was shown that you can actually realize non-abelian T-duality and fermionic T-duality using a topological defect. Good. So that's all I need about topological defects. So now let me show you, well, not quite, because I still need to, yeah.
Sorry, question. You're saying you're going to look at topological defects from the target, but the definition of topological was about the worldsheet, so...
I will come to that. It's the second half of the talk. Yes, that's a good point. Well, I mean, this will be fine as long as we are at the level of the Lagrangian, what will be in the next slides. But when we will speak about fusion, it will be handier to actually indeed characterize them at the level of the target space, but I will explain that. Okay, so, oops. We need a few details about Poisson-Lie sigma models. So Chris already nicely introduced them, but let me go over it once again. So now we'll restrict even more the class of non-linear sigma model I want to consider, and I want to consider so-called Poisson-Lie symmetric sigma models. That means that I can apply a Poisson-Lie T-duality. And so I start with a target space, which will be a Lie group, and by solving some kind of equations, you can associate to that a very special Poisson structure. And with this Poisson structure, I can construct this background with a bunch of constant E naught. And the very special things about this Lie group together with this special structure constant is actually that they come automatically with a dual group, which is denoted with G tilde, which again come with its own Poisson structure P tilde. And it was shown by Klimczyk and Shevera that you can then write down an action that looks very much like the previous one, and these two actions then generalize abelian and non-abelian T-duals. Good. So here you might be a bit skeptical, or at least like, how do I see that it generalizes abelian and non-abelian T-duality? So the quickest way to go there is actually to invoke a larger object, which is the Drinfeld double. And the Drinfeld double is, in its easier form, just the product of G and G tilde. And by specializing this choice of a Drinfeld double, you can then see how abelian and non-abelian come up. So for abelian T-duality, you do the thing you expect, right? You want your background to be tori, so you just take 2 times n tori. And in that case, as Chris actually mentioned, the 2 Poisson structure or vanish or 0, and then you get indeed the relation you expect from an abelian T-duality. And for non-abelian T-duality, you will start with a non-abelian isometry, G, and then the second one will just be a U1. And then you can work out what that means with the Poisson structure, and you get the non-abelian T-duality you expect. So this generalizes these 2 cases. Good. So that's all I need with Poisson-Lie T-duality. Well, not quite. well, it's a canonical transformation, which is important as well, which I forgot, but that makes it even well, more like the abelian and non-abelian case, which are also canonical transformation. But the thing that I really want you to remember from this bit is that this Drinfeld double is not only a nice Lie group, it also comes automatically equipped with a symplectic structure. And that symplectic structure is, well, you can construct it using, in terms of right and left Maurer-Cartan form. The details are not that important. And it's called often the Semyonov-Tchernshansky symplectic structure. So the Drinfeld double is automatically a symplectic manifold. And since that name is too many syllables for me, it will be DSTS for the rest of the talk. Good. Now, if you have questions, you have 5 seconds because I need to drink. Good. So now we have all the ingredients you need. So the questions that I raised already earlier, does there exist some kind of defect? Can we construct the defect that encodes Poisson-Lie T-duality? Then is the defect also topological? Because it is not automatic. It might also be conformal, it might be something else. And then if it's topological, then it has this nice feature of being able to deform it at no cost. Can we then say something about its fusion and what can we learn from that? And that will be the second half of the talk. So we showed that the pair that corresponds to the target space picture of a topological defect for Poisson-Lie T-duality is actually a space-filling defect. So it's a whole Drinfeld double with as two form that characterize the defect is this STS, symplectic structure. And so that means that you have this action, and then you have to compute the equations of motions. And when you do that, you see actually that on shell, the conditions boil down to you have to choose a particular solution. After doing that, the dust has settled, you can actually identify all these relations as a canonical transformation of Poisson-Lie T-duality. So it really encodes Poisson-Lie T-duality between this model and this model. And in addition, you can then, well, it's a straightforward computation that it's also topological. So we have a topological defect that encodes Poisson-Lie T-duality, and that then also has a feature of being, yes, Alex? Who has a mic? With encode, I just mean that so topological defects can separate systems that are related by T-duality, but you need still to be able to characterize that. And so this is the one that characterizes Poisson-Lie T-duality. That's the only thing I mean by with encode. Maybe I should change that verb if it's not clear then. Is good? Okay. Good. So, and actually, just by constructing this, we'll have automatically an identification of what the so-called Fourier-Mukai transformation is that associated to generalized T-duality. So what is this Fourier-Mukai transformation? So for that, I need two facts. So the first fact is that, well, since T-duality and its generalization is a canonical transformation on the level of the NS sector, you kind of know what you need to do there. On the Ramon-Ramon field, Ramon-Ramon sector, it's a bit more complicated. And one of the ways to know how it transforms under T-duality, at least in the abelian case, it was shown some time ago by Hori that it's actually implemented by this so-called Fourier-Mukai transformation. So this Fourier-Mukai transformation is just actually an isomorphism between the cohomologies of two manifolds. And it takes this form. So let me just break it down. So it takes a polyform or a one form, whatever. So a polyform for a Ramon-Ramon field. It's with some map P1, it pulls it back to some product space of these two manifolds, where there it convolutes it with the kernel, and that kernel is actually what encodes the data of the isomorphism of the T-duality, and then it pushes it back to the other manifold, and you obtain the T-dual object or the isomorphic object. So that's what this term means, roughly. And the second fact we know, we need, and you know, is that Ramon-Ramon fields couple to d brane charges. Okay, so that's the fact I need. And now we need to remember that this topological defect, well, I was able to move it around and fuse it. And one of the fusion things I can do is that I can place a boundary condition on one of the sides, and I can fuse it with the boundary condition. And so actually people in this defect community then thinking about this, like had the expectation and intuition that somehow the Fourier-Mukai transformation should be related to this fusion process. Because, well, this boundary condition is a d-brane, fusing is doing T-duality, and somehow the Ramon-Ramon fields know something or feel the d-brane, So it should somehow be related. And this intuition turned out to be true. And they could show that quite formally at the level of the worldsheets, that fusion was a kind of Fourier-Mukai-like transformation, so doing this kind of triangle. And then it was also argued at the level of the worldsheet that you also had a relation with Fourier-Mukai transformation, and a very tangible one at that. That in fact the kernel we have here that encodes the T-duality takes on roughly this form, which, okay, it has the B fields on both sides of your solution, supergravity solutions, for example. And the thing you need to add to have the kernel is the two-form field that characterize the curvature that characterize the defect. So the defect tells you directly somehow what the Fourier-Mukai transformation is. They did that for abelian T-duality, and later they also argued that for non-abelian T-duality. And so that means that since now we have the topological defect that encodes Poisson-Lie T-duality, we can directly make an ansatz for what the Fourier-Mukai transformation is for Poisson-Lie T-duality. Namely, that it is characterized here with F being this omega STS. And this ansatz actually agrees completely with the one of Alex, Chris, and Dan that they made from a completely different perspective, where they also said, okay, the kernel is the STS. Okay, it disagrees with another one, but I think this one is a bit more well motivated. Good. So, well, I just said that you can fuse this defect we have, the Poisson-Lie T-duality defect, any defect with boundary condition. That means in particular that we should be able to understand the Poisson-Lie T-duality transformation of D-branes using this defect. And this you can indeed do, and let me show you how you do that at the level of the Lagrangian. So the way how to do that is to use a well-known method to encode boundary condition using a gluing matrix. So that means that you glue at the boundary the left and the right moving sectors by some OR matrix. Okay, this OR matrix is not anything. It needs to satisfy certain conditions that won't be important here, but it's not anything. And quite some time ago, actually, the Poisson-Lie T-duality transformation rule of this OR matrix were already worked out, so these were known. And then we showed how you can realize that using fusion. So what you do is that you take this action, you perform a formal move toward the boundary, where then you get the equations of motion, and you encode the boundary condition in this way, and we get exactly the Poisson-Lie T-duality transformation rule that were derived before, but in this picture of fusion. Good. Okay. So, so this whole bit was more about Poisson-Lie T-duality. Now I want to spend some time about just speaking about fusion and how fusion happens at the level of the target space. Good. So this fusion thing has kept a lot of people working for many years, and it's quite well understood in terms of category theory and module theory. I don't need the details, actually. The only thing I want to say is that this thing is very well understood. But at the level of target space, I think it's fair to say that it's not understood at all, or it's very ill understood. And so our goal was to try a way to have a better definition, a better understanding of what fusion means, what it induces at the level of the target space. Since it should, anything that happens on the worldsheet when you have a sigma will should translate something into the target space. And the nice thing you might you expect is that if I denote the fusion process with a star, and so I'm fusing this defect 1 and with this defect 2 at the level of target space, is that when you fuse them together, you get a new defect or a superposition of them. And okay, so that's a picture because the other one was for two fusions. So now I want to just look at this, well, a particular case where I'm going to fuse the defect with some boundary condition. So, and this case was already studied in the context of Weisel-Minowitten models by Fuchs, Schweiger, and Waldorf. And there they thought, oh, okay, we have like a Fourier-Mukai transformation here. Well, the same should be true here. So what they wanted to do is actually just have an idea what this submanifold is you get after fusing two defects. And they said, okay, let's just make the simplest ansatz we can have. So we're going to use the projector as map to go up. Then we are going to take the intersection of the two manifolds. And then we're going to take the projection back. And that's what their ansatz, and they worked it out in certain examples, and it seemed to work. But I mean, this equation has actually problems. The first one is that nothing guarantees that the result of doing these things is going to give you a submanifold. The other problem is that it comes really a little bit out of nowhere. Like it has no foundation why you should write this and not something else or something more complicated. And the last thing is that you have no expression for the curvature that should be there. And so what I would like to claim here is that you can actually resolve this question by embedding this problem in generalized geometry, or more precisely into Dirac geometry. Okay, but to do that, I'll answer Dan's question, and I need actually two additional ways to have a way to characterize a topological defect. So we had already the one in terms of the energy momentum tensor, but I will explain in the next slide two other ways to do that were worked out by Kapustin and Setter, where first it's something in the product space where it boils down to a matrix multiplication, and then another one it's in generalized geometry that we will reinterpret in terms of Dirac geometry. And the reason why I want to do that is that while these two first ones are just useful to show the existence of the defect, and that's its Poisson-Lie T-duality and topological, the last one will be the one that's useful for us to characterize fusion. Okay, so the first one, I will be rather short because it's quite, well, it's not super long to prove, but you need to crack the handle a little bit. So what you're going to do is that you're going to want to have a condition which is just in terms of this product space data. So you have the background fields, so the G and the G tilde of the two manifolds, and the B fields, and then you have the curvature of that's associated to the defect that you know. And then they showed that this condition boils down to doing a matrix multiplication of this kind of doubled metric and these two form fields, which is corrected by the B term. Okay, there is something that I don't want to discuss, is that you have a technicality that you need to do that on the screen distribution. It's not important, it's technical. If you're interested, you can ask after the talk. But the point that I want to make is that this is another way to characterize. It's somehow completely in terms of targets, the product space, target space quantities. And indeed, you can also, using this matrix multiplication, show that it's a Poisson-Lie T defect and it's topological, the one we claimed. Okay, but what we really need is something that is a consequence of that, and that will offer actually a way to have like a kind of universal description of boundary condition defects. And why do we want that? Is because if we want to have an operation between the two objects we fuse, which are these defects and these D-branes, they should at least be like the same objects, because you can't have otherwise a well-defined product between them. And the claim will be that they will both be Dirac structure, as some of you actually might know for D-brane, and that's a correct way to look at it. Fine. So let me explain what that is. So the word volumes of D-branes, as you know, is characterized by some manifold in the target space and a curvature. Okay, it has many other properties, but for this talk, this is the only two data I want to capture. But defects, as I just explained, is exactly the same. It's just a submanifold, not on the target space, but on the product of the two target space with some curvature on it that capture the line bundle. Fine. Well, some people that know generalized geometry see me coming. You want, in some sense, to have that the vectors that are on the tangent space of this submanifold, you want to characterize that, but then you also want to characterize like two forms, so forms. So the thing you need is generalized geometry. So for those that don't know, so instead of having, well, I call it conventional geometry because I didn't know how to call it. Instead of having vectors, you're going to put vectors and one forms at the same footing. So instead of the tangent space, you have the tangent space and the cotangent space, which is called the generalized tangent space. And so instead of having the Lie bracket that you will have between the vector fields, now you have something which is a bit more sophisticated, which is this Courant bracket. And this Courant bracket is this form. I mean, at least you recognize one piece, which is just the Lie bracket, and then you have some terms that make it a nice bracket. It's a nice bracket, but it's not a Lie bracket because it's not anti-symmetric. Okay. So that means that here, when the underlying manifold is a Lie group, you will have a Lie algebra. Here, what you have is another object, which is the object that's characterized by this Courant bracket and other things that Friedrich mentioned last time, which is a Courant algebroid. And that's the setting in which we will be working. Okay, so now that D-branes are modeled by Dirac structure, has already appeared multiple times in the literature. It was also more explicitly described by Asawakawa, Murakami, Sasa, and Watamura, but also by Zabzin and Kerber. I will see in a moment what Dirac structures is. But the topological defect, or also modeled by a Dirac structure, was actually implicit in Kapustin and Setter. They never used the word Dirac structure, but when you read that, it is actually what they are using. Good. So now, what are these Dirac structures I've been speaking about? Well, okay, so this will be a math slide. So what is a mathematical motivation to have a Dirac structure? Well, somehow the mathematicians were in a fancy to have Poisson structures, symplectic structures, and foliation in the same object in one go. And this is Dirac structure. So what is it? Well, this Dirac structure is a subbundle of this generalized tangent bundle we just had. It needs to be Lagrangian, and then interestingly, it needs to be integrable. So it needs to close under this Courant bracket. And this is actually a very important property, because if you restrict it to the vector field, that means that this thing is going to close, and in particular is going to give you an integrable foliation, an integrable distribution. So that means that this object is going to foliate to manifold in different leaves. And let's call one leaf y, and let's probably see that thing as the defect or the debrane. And indeed, when you can show that in general, this Dirac structure is uniquely characterized by giving one of the leaves and the two form fields that lives on it. And then it has this form. So that makes it a natural object to describe exactly debranes and defects. So just give me some examples, because I promise that Poisson structures and symplectic structures and foliations are living somewhere in this Dirac structure. So let's see that quickly. So Poisson structures, in general, are not invertible, so they are degenerate. So you cannot invert them as you want. What you need to do is actually to take a point and then to see at the neighboring points, well, can I invert that? And so on the points on which it will be invertible, it will be a submanifold. And actually, this condition is going to foliate the space. And that's exactly a foliation. And so on these submanifolds, I can safely invert my Poisson structure, and I have a two-form. And this is a two-form that describes this Dirac structure. And then the integrability condition is exactly asking that the Poisson structure satisfy that its Cartan bracket is 0, so that it satisfies this Jacobi identity. And symplectic structures are actually even simpler, because symplectic structure, well, it's a two-form, it's invertible, so there the foliation is trivial, it's just a whole manifold. And asking that it's integrable just means that it's closed. So by definition, it's what it is. And more generally, you have pre-symplectic foliation, where this thing might be degenerate. Good. Okay, but let's have some physics examples. So let me give one example that most of you know very well, which are debranes in Wesel-Minueter models on some Lie group G. And so these things are characterized by special Dirac structures, which even have their own name, because they are very well studied in math, which are called Cartan Dirac structures. And they are defined by the data where, well, it turns out that you can write this definition. It's not very enlightening, but it boils down to having that Y are conjugacy classes, and that the two form, or it's pulled back by G, is this form, which is the one known for debranes in Wesel-Minueter models. So you can describe them classically by Cartan Dirac structures. And now an even simpler example, the defect we now introduced, which was on the product space, was corresponding to a symplectic manifold. So it is one of these particular examples, and it's space filling. Good. Questions? Yes, Emmanuel? Yes.
I'm a bit surprised why you need the reality condition.
You need it because otherwise you don't have a foliation of the space. No, okay. So maybe I wasn't clear enough about that. So the name topological is a little confusing because it has nothing to do with the models what it has to do. The topological thing just means that you can do fusion with them. You can move them around. So that's what the adjective topological means. Does that answer your question? Maybe, okay. Then if it's not clear, you can ask me after the presentation. Good. Okay, and so now I can explain what this third way is of showing that the defect is topological that was proposed by Kapustin, well, shown by Kapustin and Setter. So there, well, they don't call it Dirac structure, but it's the same. So there you have a Dirac structure that's describing this foliation with a two form, but nothing guaranteeing this thing is topological. The thing that guarantees it's topological is that it's stable under what they call this generalized metric. So this fancy G, was containing is this G, is like the one that was containing the two metrics of the theory. And so asking that it's topological at the level of generalized geometry is just very simple. It just asks that in some sense this Dirac structure is stable under this map, this linear map. And this is actually, for those that knows complex geometry, it's very similar to having complex submanifolds. Good. Very good. And holding a second time. Oh, yeah, Alex? Yes, so you worried because the B field does not enter in that condition? Oh, the reason is because the B field is in the 2 form. So it's not here, it's there. Okay, good. Thanks for the question. That's good. I should have pointed that out. Okay. So now we can finally get to the way we propose to define fusion in a more fundamental way that was proposed before. So we still keep this Fourier-Mukai-Light operation. That seems to be a genuine thing to do. But the thing we want now to add is just to say that, well, since both things are direct structure, well, we should really formulate and try to work with these things directly. And so that means that instead of like having this picture where I move from one manifold to the other, what we propose to do is to have the Fourier-Mukai-Light transformation at the level of the Courant algebroids of these spaces, where now the object that we are going to move are the Dirac structures, going from one Dirac structure to one Courant algebroid to the other. And so that means that we have a Dirac structure here on this Courant algebroid. We're going to pull back to this Courant algebroid. We need to convolute it in some way, which I will explain in a second, and then we need to reduce it. But okay, nothing guarantees that this is well defined in any way. And luckily for us is actually that like Cevera and some mathematicians have already worked out in what kind of constraints you need to have on these Courant algebroids to be well defined. And this are actually exactly the Courant algebroids that Friedrich introduced. They need to be exact, which is very natural for nonlinear sigma model. In addition, they need to be G equivariant, so they need to admit some nice action of a Lie group on them, which we anyways have when we have, for example, Poisson-Lie T-duality. I won't enter into details. If you're curious, you can ask, but otherwise it's just a bunch of definitions. The point is that we know exactly when we can pull back and reduce Dirac structure in a well-defined way to have a Dirac structure at each stage. Now the problem is the convolution, really the thing that's going to encode T-duality. And so the thing that we thought, well, actually let's just do the simplest thing we can imagine, and you have a product operation actually on the space of Dirac structure that you can find in math literature. And that I denote with this circled star, and okay, it takes this form, and so it lives normally in the intersection of these two manifolds, and then you have this very simple form. And okay, with certain smoothness conditions, this is again a Dirac structure. Oh, good. Now it seems that we have all the ingredients. So the result of doing that, so the fusion operation we postulate is actually exactly this: that you have this Dirac structure, you pull it back with just the inverse embedding map, you convolute it using this product, and then you reduce it to the fused manifold. And then the resulting object that you have at the end of the day of doing this is this for the submanifold and this thing for the 2 form. And as you might have noticed, this is exactly the fused word volume that Fuchs and Schweigert and Waldorf had, except that now it's well defined because we know that we always will have Dirac structures if we cook within this well-behaved class of object that we expect anyways. And we also have a formula for the 2 form fields living on that gives a consistent Dirac structure. And okay, it does not come out of the blue this time. And you can actually check in the language of Cevera of Poisson-Lie T-duality in terms of Courant algebroids, where he actually has a section about how to do Poisson-Lie T-duality of Dirac structure that represent the D-branes using these reductions. And it's exactly the same as well. Okay, so yes, Dan? Yes. It's in F. Well, I mean, it's in this F. It's here. So actually, okay. So when you look at the Fourier-Mukai transformation, it's formal form, because it always takes actually a more complicated form, but it's always spiritually like this, is the K. Well, okay, K plus the B fit. Okay. That's. Let me then summarize and give some outlooks. So I argue that you can realize Poisson-Lie T-duality in terms of a topological defect, and that gave us like a free lunch to have an ansatz for the kernel of the Fourier-Mukai transformation, which coincides with one that's already known in the literature. And then I explain how you can use this fusion process to have the T-duality on D-branes. And then taking a step back from Poisson-Lie T-duality, I argue how one could define a fusion operation at the level of the target space, which is well defined and coincides also with the known cases. Good, so some open questions. Okay, so the first one, it needs a bit of background, so I need like 2 minutes for this one. So I already mentioned that Fuchs, Schweigert, and Waldorf have studied quite a lot topological defect in Wesson-Minowita models. And as I mentioned, in D-branes, now I'm speaking about D-branes, in Wesson-Minowita model have this very nice picture that the submanifolds, they correspond to our conjugacy classes. And what they obtained for what the submanifolds of topological defect by some scattering computations on the world sheet was that the world volume of these topological defects are bi-dressing orbits, bi-conjugacy classes, sorry. So it's very nice. It's like you get a kind of mixed conjugacy class in the product space, and that realizes your topological defect. And so as Klimczek and Schevera showed, is that you can see the world volume as D-brane, Poisson-Lie T-duality, as dressing orbits. So dressing orbits are like nonlinear generalization of conjugacy classes. They are complicated conjugacy actions. But so the natural thing that you might expect then is that the topological defect in general for Poisson-Lie T-duality will be bi-dressing orbits. Well, we tried a little bit, we failed, but I still haven't given up on that idea. Okay, then another thing is that, so I told you that we studied integrable defects in Yang-Baxter models. And integrable defects are actually very special cases of topological defect. So you might wonder, okay, can I also fuse these things? Well, it's also tempting, but it's actually very complicated because the problem with defects in all these different contexts is they all have their own definition, all they have their own construction, and it's very difficult to relate them. But maybe there can be a way to do that, and that would be interesting. Okay, okay, the last two are more contentious, and it's more like if you find that interesting or if you have any insight, please come talk to me. I would be interested to get more insight on these things, whether it's even possible. So I only spoke about fusion of a topological defect with a boundary condition. I never said anything about fusing two Poisson-Lie T-duality together. So why I did not do that is because we are still computing things about that, and it seems to be puzzling. Because while for normal T-dualities, you will always get that it's again a T-duality, and that it's again topological, for Poisson-Lie T-duality, it seems to be more complicated. And so that might point out that at least maybe at the level of fusion, Poisson-Lie T-duality is quite different from abelian T-duality. But that's okay, it's very preliminary. And then the last thing, which is probably even more contentious, but it's interesting to think about, is that, well, this fusion, it's not difficult to guess that you can see it as a kind of solution generating tool, right? You're in a system, you cross a defect, you get another system which is related by symmetry or duality. And okay, it was also studied as in this form by Bachas, Brunner, Sato, and Sagawara. And in particular, these people studied that in the context of generating non-geometric backgrounds and also T-fold. So one might hope that one can maybe have a step towards these things using fusion. But okay, this is okay. So thank you very much. Stop. Thank you. Advertisement. So I would like to draw your attention to a school, which is a young researcher school and workshop. So if you don't know this is a school that normally is every year, and that focuses on a particular topic, mostly in integrability. And so this year topic is about an exact approach to the string worldsheets using CFT techniques and integrability. And this year it's going to be the last week of October in Stockholm. And so it's aimed towards a PhD student and starting postdocs, young postdocs. So if you're in this demographic, I strongly encourage you to go and check out the website. And if you're not in this demographic, go do that anyways, and please advertise. Okay, that was the end.
Thank you for that nice talk and advertisement. So do we have questions for Saskia?
Yeah, hi Saskia. Thank you for the very nice talk. It was very interesting to see this approach from the other side, so from the defect side. What I wanted to check with you, did you calculate the transformation rules for RR fields from your kernel of the Fourier mechanic?
No, we did not do, but that's a very good point. Like
because I was wondering, I mean, so when we did this back then, you know, this was exactly our starting point, and we were saying we know the RR sector transformation rules from solution generating techniques, and then we were just taking them to calculate the kernel for the Fourier Mouquet transformation. And I mean, when you say they are different, then there are two possibilities, right? Either there is some subtlety. I mean, probably there are some possibilities and some choices for the kernels which result in the same RR transformations. Or, I mean, there are three possibilities. Or, I mean, you get different RR transformations than we already got from imposing solution generating techniques. Or we did something wrong. I mean, so some computational mistake.
Okay. No, that's a good point. Thank you for raising that. Actually, my guess would be the last one, because and the reason is as follows. So if you look at this operation, so this P and this P2, like in the way we computed it, it takes a Fourier Mouquet transformation where it's this funny integral that just kills all the one forms that are of lower rank, and because of that, you lose a lot of terms as well. So we did like a sort of back engineering, but doing this back engineering, we potentially lost a lot of terms that we didn't see at the end of the day. So in there, I think it's one of the reasons why it doesn't match. But then, indeed, it seems puzzling that these two things at the end of the day give the same result. It's in under some terms are redundant. I don't really know. And maybe the other different Ramon fits. I didn't think about that option.
Yeah, because I mean, when you say it's really a different result, you know, so you should get perhaps different transformation rules for the Ramon fields. And then, of course, it would be interesting, because it's all connected to D-branes, right? I mean, we were more taking the effective field theory perspective, while you are really taking the nice classical D-brane approach. I mean, because from the classical worldsheet theory, you normally don't get the RR field transformations. So that's why it would be really interesting whether this gives different RR field transformations or whether there is some freedom in this kernel, you know? Yeah, and so that's why it looks like they don't match.
Actually, this Fourier Mouquet thing is very mysterious also just from a mathematical point of view, because mathematically, this Fourier Mouquet transformation is studied a lot by mathematicians, but in abelian context. And when you ask them about a non-abelian context, they say, and they just leave it in peace. So that makes it probably also complicated because there are no formal results on that once we want to move to Poisson-Lie T-duality. Yeah, no, I agree. It's a very interesting question.
Other questions?
You said your fusion was a bit funny for the Poisson-Lie T-duality. Could you elaborate on what exactly happens?
I can say that off camera because I don't want to be on video if it's wrong at the end of the day. I would.
And then could you maybe just say again, what in the target space, what was the defect that encodes the Poisson-Lie T-duality? Because it's not the D-brane. It's not a D-brane, right? So,
no, I mean, like the big difference between D-branes and defects is that they don't even live in the same space, because one is on the target space and one is on the product space. So it's why like the defect is living here and the D-brane is living there, and that's the thing you lift, and there it's then you can convolute it with the defect, and then the result you just push back.
Okay, thanks.
Yes. Okay, thanks for the question.
Thanks for the talk. Can you elaborate on this screen condition that you have? You said it was a little bit technical, this GF square equal 1. Can you elaborate on that?
can you say which?
This condition you have with the generalized metric and the flux that the square of that is equal to 1, you said that perhaps you can elaborate on
Yeah,
the.
it's just because you have a DD signature. Your space on the space is not going to nicely divide into the tangent and the normal one. You have, and the thing that you miss because you have this mixed signature is called the Screen distribution. And it just turns out that when you do the computation that Setter and Capucin did, is that the condition is on that Screen distribution exactly. So it's just a technical detail actually.
Okay, thank you.
Hello. I have a question about the slide that you just flashed in, and about this model that you have, about the S1 plus S2.
Where do I have S?
Sorry, I mean when you interpret Poisson-Lie T-duality as a in terms of defect.
So the very last one?
There was like an action that you wrote that it's like two terms and then you had the pullback of the connection. Yeah, sorry, I don't remember where that was.
Maybe you can show afterwards.
Yeah, okay, yeah, sorry. Yeah.
Okay, no problem.
Any more questions? I don't see any other hands, so if not, let's thank Saskia again.